think for all of us in the room, it's been a busy couple of weeks dealing with our own personal issues after the event. For many of us in geosciences, many in engineering, there's also been a lot of work to be done to try to characterize the event while the information's still available. So a lot of this is very ephemeral, but it's crucial data, and as I go through this, I hope to give you a sense of the type of information we're going after and why it's important to get. Well, and also, we've all seen these pictures all over the place. Let's turn the lights down a little. Let's see. Yeah. And I'm not going to focus really on the damage in the main city. I think people have seen quite a bit about that. Rather, I want to talk about what happens during the earthquake itself, what information we're getting as we go close to the fault and in the vicinity of the fault, because that's telling us a lot about the information, the energy source that is what caused this damage far field. And if we don't understand the energy source, it's really hard to understand the consequences. And so if we look at a map of the region, Christchurch is here. We're somewhere up in this neck of the woods right now. Here's Ilam and Riccarton. The main fault is essentially east-west, extends for something like 30 or 40 kilometers, starting somewhere over by the village of Greendale, and extending over to somewhere a little bit north of Rolleston. But I've shown this sort of dog bone shape because as we get to the ends of the fault, we see that it tends to splay out into a less well-defined zone. But there are some other hotspots of activity, the town of Hororata. I'll show you some things from out here on the Methven-Darfield Road. And also I think people know of all the issues related to liquefaction in the main downtown area. But what we did first is, try to find the fault. So we were woken up on the morning of the event and had daylight, and I worked closely with people at the U.S. Geological Survey in Golden, Colorado, which is the National Earthquake Information Center. They're the global seismologist part. And if this hadn't happened in New Zealand, but it happened in a less well-established science country, they would be the ones who would take the lead on it. So they are the ones that are responsible for earthquake information and trying to understand what's going on for any global earthquake, any significant earthquake. So I work with them. I have a partial appointment with them. So they were able to, it was whatever, 4 o'clock in the afternoon, 2 o'clock in the afternoon for them in Denver. They were telling me locations. So we got in our vehicles to look for the fault, to try to map it out, to get a sense of where it is, how big it is, how much offset. And, they basically drove out along the road, stopped in a few houses that were damaged. The people pointed us. They said, well, Telegraph Road's got some problems on it. Went over there and essentially found the fault. And from there on out, we've been mapping it along the way. And so this is this is now probably almost a week-old version of the map of the fault. It's pretty straight. The thing that every spot that's on this map is a place where it's actually been observed breaking the surface. And you say, oh, of course, an earthquake breaks the surface. That's not the norm oftentimes. So for an earthquake of this size and this nature, to have this much of a continuous surface break is not the typical behavior. Typically, there will be splotches of it, a kilometer here, a kilometer there, but this is effectively, one can almost walk from one end to the other, continuously following the trail. Now, partly it's because there's a great system of fences on the paddocks in Canterbury, and most of them used to be very straight. The farmers take pride in their fences. They were well maintained. They weren't falling down. And so they've become incredibly good scientific markers. We can actually survey them in. The pre-earthquake positions were well constrained, and they're giving us a lot of information. But also, as you'll see in some of the photos, there's a lot of damage to the fields themselves. This is an issue actually for the farmers to deal with. How do you close up all of these holes in the ground in an effective way? But we'll take a little tour of the fault in some of the different spots along here and see, what it looks like. Some of you have probably been out to these sites, but many haven't. So this is Highfield Road. This is in the vicinity of where we've observed the maximum offset, more than 4 meters of horizontal displacement. To put that in perspective, that's large. For this size fault, it's large. For this size earthquake, it's large. It's on the large end for a magnitude 7, 7.1 earthquake, but we'll get to what size means in a bit. There's also about 1 meter of vertical displacement here, and this was sort of became the photo op site. So if you're watching the news, TV1, TV3, this was sort of where they tended to set up. There was the farmer over here lamented that he didn't set up a little barbecue and sell sausages. He probably could have made up all of his losses with the number of people coming through. But it's a very dramatic site, and as an earth scientist, I look at this and say, wow, that is a very impressive fault offset. It's over a relatively narrow distance. You can see the road is virtually perfectly straight here. And if I turned around and took a picture the other way, it was also perfectly straight. The locals said this was sort of the local boy racer. Straight away, 160K, no hills, no turns. Well, now it's no longer. It's more like a, I guess, adds more challenge for the boy racers. So this is a very dramatic effect. And as we move along, so this is in this section of the fault. If we move over to the west a little bit along the fault, there's this interesting little pine plantation. Family lives in here, and these are probably 20-year-old pines. And you can see the disruption of the Earth's surface through the pines. These, again, were nicely lined up, planted well initially. Now they're offset. So we went out the first morning and saw this and mapped out its orientation to try to figure out how to follow it. But a few days later, we came back, and it was like, and we're saying, have we missed something? Because when we came back, all the trees had fallen down. And they didn't fall down during the shaking of the earthquake itself, but the earthquake shaking damaged the roots in a way that Sunday night, Saturday night, or Sunday night, there was a strong wind came through, and the trees that were right along the fault zone, within this 20-meter wide zone that was the fault zone, fell over. The trees on either side of that are happy as clams. Now this becomes actually important because one of the tools that people are using to look for old earthquakes, and particularly on, say, the west coast along the Alpine Fault, is tree ring data. And if you go and you have trees that are alive, well, an event like this disrupts their roots. And so they, even those that are still standing, may go through a year or two of stunted growth because their root system has been disrupted and they're going to have to bring that back. So that is actually a data set that's being used and has been used globally to actually pin this down. Now, some people are suspicious of that type of a data set, and so I think this is proof positive that yes, if you're near a fault and you're a tree, your roots take it in the shorts. So it's something, an evidence of that. Now there were several houses, you may have heard about some of them on TV, that had the really unlucky distinction of being located exactly on the fault zone. Now, you can go through the odds of that and compare that to the odds of winning lotto, and I think lotto is probably a better deal. You probably have a better odds, and also the prize is somewhat better. But these folks here, and these folks raise greyhounds. They had about 70 or 80 greyhounds for racing. And their house is, basically we can follow the fault through the paddock. It goes through the house, around, splays a little bit around it. We were out there with some of the structural engineers from civil engineering here. And it's amazing the house is still standing. It's brick clad, but it is a wood frame house, and wood frame houses tend to do better in the shaking, but it's straddling the fault. But essentially nothing pretty much collapsed on the fault zone itself. There was a lot of shearing damage just because of the actual movement of the ground. But it almost implies that the ground shaking may have been slightly less severe right within the fault zone. And that's something people have looked at in terms of the so-called tunneling waves, that actually, so a lot of the energy may stay and be propagated through the fault zone itself and not make it to the surface in a wide zone. But once you get away from the fault zone, you experience stronger shaking. But these folks, their house is basically sheared in half by being straddling the fault. Now, as I said, the fences in Canterbury are a spectacular research tool to be able to really define precisely, probably to a couple of centimeters, what the amount of offset is at different locations. Here's an example. We're measuring this with a kinematic GPS system. But this fence here and this fence here used to be perfectly connected. So everything, it's not just that things moved along the fault. Everything on this side of Canterbury moved 4 meters relative to everything on that side of Canterbury. out by the fault. So when we think about faults, the energy is not just what's in the actual differential motion place, but large volumes of the Earth have shifted their position during the event. And so, you can follow this, and there's also, in this case, about a half a meter of uplift. So we were able to follow basically this just along, and it was right in here that we found, again, there's a spot of about 4.6 meters of displacement measured across one of these fences. And so, 4.6 meters, well, that's halfway from, well, maybe, more than halfway from me to the wall there, right? So it's a significant amount. And that took place in that actual shift took place in a couple of seconds. So although the earthquake itself lasted for 20 some odd seconds perhaps, at any one location, most of the displacement took place probably in less than 10 seconds, more like 5 based on our models of the earthquakes. Here's just one of the roads out here. This is, I think, Milton, and it's, again, offset by about 4 meters, and the pine forest over here and into the paddock there, you can follow it. We can follow the trace on both sides of it. And you can just see here, we're laying out a tape, the distance that this road and this road have been offset. Now, there was an intriguing result we saw which baffled us initially. Immediately on the TV, there were helicopter pictures of the railroad track that was buckled, and many of you saw that. And this railroad track is near Rolleston. It's on Railway Road that's going sort of northwest out of Rolleston. It's a line that goes to Darfield and then up over to the west coast. And it had a kink in it, and we got there after they were repairing the track, but the kink was in the wrong direction. It was what we call left lateral. It was bent to the left rather than bent to the right. And this was a bit baffling, and we see after they've replaced the section of track, you can see the track is bent to the right, which is what we'd expect for the type fault. And so initially when we went there, it's going, wow, people were thinking, is there 2 faults involved? You may have heard on the news, maybe there are 2 faults because they were watching, we had evidence of the right offset fault, but there was news media talking about a left offset, or people were seeing this, and should we go look at this? Well, so they replaced the track, and when they replaced the track, they had to cut about 4 meters of length off their standard length rail to fit it into the hole that was left now after removing this. So the tracks had shortened by about 4 meters, and that's essentially what caused the buckling, and so the direction of buckling was irrelevant to the story. What really went on was the shortening, and the shortening is because this is at the eastern end of the fault, and it gets to be a much broader zone, and so the railroad track isn't necessarily being cut by a single discrete nice fault, but it's in a broad shear zone. And essentially, the track is being rotated clockwise as the north side of this keeps moving to the east and the south side keeps moving to the west. And if you try to rotate this clockwise in a fixed zone, it has to shorten. And so it shortened by about 4 meters. They had to come back 3 days later and cut another 2 meters out because it was continuing to shorten. And so we are concerned that there is, we're not concerned, this is typical of these types of earthquakes, what we call post-seismic creep, post-seismic slip. And so we've actually put out some surveying marks to monitor this over the next months. But this is after they had actually repaired the track a second time and brought a machine in that straightened the track. It was an amazing locomotive-like thing that came in, would lift up a section of track, sight it down a laser to a point they had, and shake it around and place it back down in the correct place. So they had this almost perfectly straight, so it looked about like that, and you come back 2 days later and it looks like that again. So, they're continuing to have to repair this. Now, part of this may simply be relaxation of the track itself. I don't know the physical properties of railroad rail, steel, and there may be some elasticity in that that's playing out. But we are monitoring this sort of a site. But these are the types of clues we have that can help us get at displacements, etc. Now, when we move away from the fault itself, there were some weird things that people have seen. And for example, the church in Hororata, they had a lot of shaking there, but yet they're not adjacent to the fault. And so that's a little bit of a concern. Why does the fault continue subsurface and didn't? Because remember I said that it was almost extraordinary to have so much surface rupture observed. So, the fault may go further than that, and I'll talk a little bit about that in a second. But also there's strong shaking. Now, part of it is it's, the Hororata River, the Selwyn River, all these things are in that part of the world. Things built on river sediments sometimes can have amplification of shaking, liquefaction issues. I mean, these are things that everyone in Christchurch is now becoming quite expert on. But there are some other intriguing things. For example, in the graveyard behind the church, all the gravestones that fell to the west. So that's telling us something about, potentially about the strongest motion that caused a gravestone to fall over. Now, not all of them fell over, but these are issues to think about, and if we can compare these to some of the seismic records, we can get a sense of the nature. Because, so we'll see in a second, there's some other interesting things even further to the west that may be related to the event, and I'll speculate on that in a bit. And that's this here. This is now basically on the backside of just on the other side of this ridge down in a valley over here is the highway between Darfield and Methven, or the Rakaia Gorge Road, one of the 70s. 77, 73, I don't know, I get confused when I get out there which one goes exactly where, but one of the 70s. Well, this is a ground breakage observed along about a 4-kilometer stretch of the hillside. Now, partly it could be just a landslip type headscarp. Many of you probably have seen those sorts of things, but it's continuous for quite a distance. It was generated during the event, and it is also consistent with the idea that there could be a small, what we call thrust fault, and I'll get to some of those explanations in a second, that caused this side here to move up relative to that side, and the surface cracked on top of it. This becomes important. It could potentially be related to triggering the event. It also tells us something about the overall state of stress in the Canterbury Plains that could be responsible for the event. So this has been mapped out. It's now been staked. You may have seen a picture in yesterday's press that showed a couple of the postgrads in the department who are surveying across this, trying to map to see whether it's continuing to move, et cetera. But it goes for quite a distance. And on the backside of that, along the road, this is the road between Darfield and Rakaia Gorge. Major failure. I mean, this is down, this guy is 180 or 185 or something in height, and it comes up to his shoulders. So, there's been this is quite a distance now away from the main fault. We're talking 30 kilometers away from the end of the fault or something like that, and yet there's significant damage here, which implies there may be other features, maybe other structures involved during the events. Okay, and I'll just take a couple of minutes, and then I'll get back to the seismology of this. This is a map that hopefully many of you have seen, or if not, you will check it out. This is a part of a poster that the Regional Council has produced showing liquefaction hazard in the greater Christchurch area. They have different versions of the map. This is the high groundwater table liquefaction conditions we're at right now, end of winter, high groundwater table. And you can see, it documented a lot of the areas that in fact did suffer liquefaction. Liquefaction, the structures we see are not related directly to the fault, and people talk about fault lines going through their property. Those are surface failure zones. They aren't fault zones themselves in any sense. But you see pictures like this, and the TP structures as the subsurface has collapsed and there's shortening on the surface, and lots of damage. And so although this looks like there's been motion on a fault, this is simply due to differential removal of material underneath things, and as they fall down, they also move laterally to fit in the space. And this fellow is not having a good day. But so these are some of the liquefactions. The other big thing are these so-called mud or sand volcanoes that are associated with this. So when the liquefaction occurs, it's not just that things nicely flow away. They actually shoot out of the ground as geyser-like features, and they form these things that look like volcanoes. But you could see cars from that part of town that had this light gray sand on their roofs. So it had shot up into the air and then landed on their roofs. There's a lot of energy involved in this liquefaction, and that's basically the energy of the shaking, forcing causing a pressure increase that jets this stuff out. Now, in general, it tends to be, at least in the Kaipoi and Avonside areas, it tends to be mostly this fine sand, but that's not the case everywhere. As you get near some of the other areas of town, some of the things that are ejected here are quite impressive. Also, this is now a photo Mark Quigley, colleague, took the other day from a helicopter there following the fault. So you can see the fault running beautifully across here. Sometimes there are what we call step-overs, so the fault comes along here, offsets this, and then heads off that way. But all these little grayish things. Those are these sand volcanoes, liquefaction things. So this is now out in the middle of a paddock. So this is not just areas like Havenside or parts like that. So there's a lot of that going on. Some of this, I mean, most of Canterbury is old river bottom of one form or another, and so there's pockets of fine sands and gravels, etc. This I found very intriguing. So this is at the golf course in Greendale. So the fault's somewhere up here, you know, a couple of kilometers away. We went there, and the groundskeeper took us around. They had a lot of liquefaction damage. They're on the banks of the Selwyn River, but they're not, you know. Well, this here, we have a couple of things I think that are very important. This chunk of sod, which is, you know, this big, it popped out of the ground and landed there. This wasn't dug out by the groundskeeper. It was ejected and thrown there. And this thing probably weighs, I don't know, 20, 30 kilos. It's a big chunk of dirt. I mean, it's heavy. And it was ejected and landed there. But what it landed on top of was a deposit of other liquefaction ejected material. And here we're seeing not just that fine sand, we're seeing cobbles bigger than your fist. So I would not have wanted to be here at 4:35. I mean, this would be like a war zone. There would be stuff falling out of the sky that's, you know, rocks of that size to get ejected, and then to have this thing pop up and fall down. I mean, that's a very impressive sight to see. And so, I mean, these are things we can now work backwards and say, okay, what's the physics of this? I mean, you know, you can have the theory, but now it's like, okay, what is the actual physics? What forces are necessary to cause this? You have to break its connection. You know, grass is intertwined root systems. You know, you try to dig in your yard, and you have to break those root systems to get it to move. This thing popped out as a beautiful, discrete chunk. So these are the type things we can say a lot about. And you just see these spectacular pictures, and sometimes the fault zone gets a little broader, and in those cases we have these diagonal shears that connect it up in the step-over zones. This is a picture from 1906, the earthquake, the famous San Francisco earthquake in 1906, and this looks pretty similar to what we've been seeing, you know, same type of thing. So what I want to do now is take about 5 minutes on a brief tutorial about earthquakes, magnitudes, what earthquakes are like in various ways, so we can look at some of the other types of information we're getting that may not be totally familiar to all of you. And at the end of this, you can call yourself seismologists. You know, so we'll just look at a couple of things. Now, first off, for the geology 112, 111, 113 students, who, if there are any of those around, this should be old hat. But basically, there are different types of faults depending on the sense of motion. The types that we're mostly interested in here are the so-called strike-slip. They can either be right lateral or left lateral. This is what we have as the main fault. We also have faults that we call thrust or reverse faults, where one side is thrown up over top of the other. This might be the sort of thing I said we were seeing in that area out by the Methven Darfield Road. And so these are sort of two different types of faults. Now, one of the things is when an earthquake moves along this fault, it radiates energy. And the nature of the energy that's radiated is different depending on which side of the fault is on and what direction the motion actually is going. And this is what is recorded by seismometers globally. So even far field, we can work backwards. And this is the information I was getting from my colleagues at the USGS at 5 o'clock in the morning. They can tell us what the nature of the faulting was. And basically, they could say it's either going east-west or it's going north-south. So look for east-west things or et cetera. So with that information, we can determine what the fault orientation is, the sense of motion, and we make these figures that people call focal mechanism, fault mechanism, beach balls. They go through a variety of names, but basically they have characteristics, and what these represent is the nature of the energy that left the earthquake. If they're colored in, it means the energy left and it was initially compressional. It was a shortening mechanism. So as this is moving, say, to the east, anything to the east of it is being compressed, is being shortened. And so it would be colored in that zone. And if it's white, it means that the initial motion was being pulled away. And so that energy is recorded on the seismometers. We can map that out. It also affects the entire seismogram. All aspects of the waveform are affected. So we can use that to come up with this. So this is what the main mechanism looks like for that earthquake. The red zones are the compressional, the white are the what we call dilatational, the extension zones. And so we see that this says that the north side moved from west to east, and the south side moved from east to west. Now, it could also be the opposite this way, but we didn't see any north-south faults. We only saw the east-west faults, and there's other information. So we can use this with a lot of other information to really start pinning down the nature of the rupture. We can see it on the surface. We can map out the displacements. This is one of the few of this size events that we can have such a detailed surface rupture. We can also use the data being recorded on seismometers, both regionally and globally, to pin down where that energy was physically coming from on the fault surface itself. Faults are not nice uniform things. They have pockets of high energy release and pockets of lower energy release. And so we'll talk now about that and magnitudes. You know, everyone's becoming an expert as a seismometer. We all know, you know, an aftershock comes, and every office I've been in, people saying, what do you think, 4.1, 4.2? You know, there's supposedly office pools all over campus on that. I saw in today's press, they had a cartoon about, instead of the lotto, they're going to have something where you guess the sequence of aftershocks, and then you win the prize if you get the correct magnitude sequence. But there's a lot of different terms that are used for magnitude. And you know, when we talk about how big an earthquake is, we tend to use magnitude. There's the so-called Richter magnitude. There's something that's more related to the rupture area and displacement called a seismic moment. And we'll get to that. So the Richter magnitude, this was invented in the late 20s, early 30s by Charles Richter for Southern California. He had a particular type of seismometer called a Wood-Anderson, haven't been made since 1932. And for that particular seismometer, he said if you're 100 kilometers away from the earthquake, a magnitude 1 earthquake will have this amount of ground displacement. And then he did a log scale, and he came up with the Richter, what became called the Richter magnitude scale. Now, although that term still is used, there is no such thing as a Richter magnitude. There are about 30 different types of magnitudes, all depending on what part of the seismogram is measured. And so there's something called MB, which is measured in the first few seconds of the event. It's a local magnitude. There's an MS, which is measured using the surface waves. There's an ML, which is measured using another part of it. And they all sort of get thrown together as being called Richter magnitudes. The problem with the Richter magnitudes of these types is that they only work over limited magnitude ranges. They tend to get saturated at different things. And so, for example, here are two earthquakes. One's a 6.1, one's a 7.7, and yet they have identical MB, because the first 5 seconds of those two earthquakes are similar in size. This one only gets bigger 10 or 15 seconds in. And so the main way that's used now is something that's called a moment magnitude. It's written as MW. And so for the big one, the 7071 number, that's a moment magnitude. It's determined in a totally different way. The nice thing about that is you can go directly from a magnitude that the seismologists determine using seismic instruments globally, but it's related exactly to the rupture area, the area of the fault, times the amount the fault slipped, times the physical properties of the fault zone, the so-called shear modulus, how easily it is to shear the rocks in the fault zone. We know the shear strength of rocks. That's been done in laboratories for years. We went out in the field. We could calculate the rupture area. We walked it out. We measured the slip distance. So we could actually determine a seismic moment, and thus a moment magnitude, simply from the geological observations, which could be compared then to the moment magnitude that the seismologists were determining based on global data. And they're the same. That's really important. That's telling us that the fault we're seeing is basically the fault. There isn't a whole lot of hidden fault somewhere else. You can hide small faults elsewhere, but you can't hide another big fault anywhere for this earthquake. So the moment magnitude observed geologically and observed seismologically is identical. And that's not always the case. Oftentimes you will not observe nearly as much surface faulting. The bad news of that, one of the reasons we're observing so much surface faulting, is that most of the rupture was shallow. And that's why it did a lot of damage. That's why it's been quite strong. Now, another thing that people bounce around is a so-called intensity scale, modified Mercalli, and that's a local thing. That tells you how much shaking you experienced in a spot. Well, basically, everyone in this room who was in town experienced something in the Mercalli intensity 7 to 8 range or higher. Heavy damage. I mean, we've had less damage than that, and this is something the engineers are trying to understand a little bit is that shaking, it's not that the earthquake didn't cause the shaking, it caused the shaking. Its building stood up a little better. What is the reason? And they're thinking it could have something to do with soils. Obviously, building codes matter, but there's a lot of things. The Mercalli intensity scale is different from the magnitude. Magnitudes are for the earthquake. Intensities are locally to you. It's what you feel in a spot. Whereas the magnitude of an earthquake doesn't change. The intensity changes as you get further and further away. Now, the other question that keeps coming up is aftershocks. When are these blah, blah, blah aftershocks going to end? Well, not for a long time, but here's a plot from some other earthquakes in Southern California. The Landers earthquake was a little bit bigger than the one we had. The Joshua Tree was smaller, 15-kilometer rupture, 85-kilometer rupture. This is the decay of numbers of aftershocks with time, and you can see that this goes on for a year afterwards. But if you read the key, these are for magnitudes 2.5, magnitudes 2, magnitudes 1. In Southern California, they can locate earthquakes down to magnitude 0 because of the number of seismometers they have. And so, but if you think about, the magnitude greater than 2.5 died off in like 30 days after a bigger event. So, we're going to stop feeling them, but they're still going to be cranking along. The seismologists will locate them, but they won't be things that necessarily you'll feel. But, every so often in one of those, there'll be a slightly larger one to pop off and, going, oh, geez, what's going on? And, in the same way, we're now mostly having these 4s, right? 4-1, 4-2, 4-4 for the last couple of days. If we had a 5, 5-2, that wouldn't be out of line with the normal decay pattern seen in other earthquakes. So, it's not meaning the end is coming. It just means that's the normal procedure. So, but they do tend to decay off in time. The number of events, the timing between them, et cetera, dies off. The other big thing about faults is that they aren't a spot on a map. Their fault has a length to it. This fault was about 35 or 40 kilometers long. It started at a point which is the hypocenter, or sometimes referred to as the epicenter. It then ruptures away from that point, maybe in one direction, maybe in both directions, and it ruptures at a rate of about 2 to 3 kilometers per second. So our 30-kilometer long, 40-kilometer long fault took something like 20 seconds to rupture. That's why the duration of the earthquake was 20 plus seconds that you felt, because once it stopped rupturing, it stopped radiating energy, and then eventually you stop feeling it. It bounces around a bit, it echoes a bit, so to speak. But the deal is, it takes that. And so our event was about probably 10 kilometers vertically, about 30 or 40 kilometers horizontally, and it ruptured at about 2 to 3 kilometers per second. So it's a plane. But the rupture isn't simple. And in fact, there are pockets of energy along the fault, sections that had a harder time breaking, perhaps, and they radiate more moment, more energy. And so those patches can be observed, and we can actually map on the fault where they are. We might expect those to be spots where we have larger offset on the surface. You might expect those to help control where some of the ground shaking is more severe, et cetera. And so one of the things that can be done is we can map the offset on the surface. We can also go using seismology, and this is an example from the Denali earthquake, and we can map what we call asperities. These are blocks on sections on the fault that take a little bit more to rupture, and when they do, they release more energy. It's very typical for all faults of this size and larger to have multiple ones. This is the Sichuan earthquake of a couple of years ago. It ruptured from the south to the north, and there were 2 big pockets of energy release storing it. It's slight different motions, but that's case. And these we call finite fault models. And these basically what they do is they take all the seismograms from around the world and break it up and break the fault plane up into little blocks and treat each of those blocks as having a smaller earthquake on it. And they just calculate, it's essentially just a linear programming exercise. You have Green's functions for each of these blocks. For the math guys in the room, you have your Green's functions, and you basically have a search to put together something that will regenerate all of the seismograms that you see globally. And with some constraints, and I'll show you some examples from our earthquake for that. Okay, the last thing is in terms of relative size. Here's different earthquakes, relative things. So these are some of the ones, the famous North American ones, relative to the Sumatra earthquake. The Alpine Fault, the one that everyone talks about, would be about that size, a little bit bigger than San Francisco. Our earthquake here is about the same size as Loma Prieta, not as long, but it had big slip. So, since remember our size is both area of the fault, but times the slip of the fault. This one had more slip than Loma Prieta, but it was shorter. So it sits here. Now, I did a couple of quick calculations. Needed this for What Now on Sunday. We did a little bit on the What Now show. It ends up that during this event, there was the equivalent of 2 billion millibars of energy released. That's 2 times 10 to the 15th joules. Maybe for this audience, on that show, then they said millibars, and they threw all the kids millibars, get their sugar level up to keep them lively for the rest of the show. But that's also equivalent to 1 day of New Zealand's energy consumption across all. The total energy usage in New Zealand, industry, personal, all of that is about 2 times 10 to the 15th joules. That was same amount of energy that takes you guys 24 hours to do. This fault did it in 20 seconds. Way more, overachiever or something compared to the normal New Zealander. But so that just gets you a sense of the energy we're talking about here. This is a lot of energy. This is, and I think this is more useful, millibars particularly, than saying it's so many atom bombs or something, because most of us don't have a whole lot of experience with atom bombs. We do know the sugar rush we get from a millibar. Okay, one last thing in this, and then we'll get to some of the seismology. One of the truly amazing things about this is the fact that there were no people killed and very few people injured. Here are the statistics on number of fatalities versus magnitude of an earthquake. The Haiti one is way up here. This Wenchuan, the Sichuan event probably should be up there too. There's some question about whether the data are dependable on deaths in the Sichuan case. I mean, the Canterbury event is off, it's down infinitely below here since there were 0, and I'm on a log scale. But the point is, we should have expected for this size event in normal behavior somewhere in the 100 to 1,000 number of fatalities, and we didn't see that. And that speaks highly to a lot of things, the time of day, construction, people doing smart things, there's all sorts of things played into it, but it's a truly amazing thing and a very positive aspect of this. Okay, so let's get back a little bit at the end to the event itself. The key thing to remember is New Zealand is a plate boundary. Not New Zealand is next to a plate boundary, not that a plate boundary goes through New Zealand. New Zealand is the plate boundary. Everywhere in New Zealand is feeling the effects of being part of a plate boundary between Australia and the Pacific. And the nature of how that is felt is different in different places, but it's because of that, in fact, that New Zealand is even here. Because it's the shortening that's occurring, the deformation associated with the plate boundary, that has actually elevated these undersea plateaus, the Campbell Plateau, the Challenger Plateau, et cetera, and made them thick enough across to be above sea level, so there's land here. If it weren't for the plate boundary here, most of this would be submerged, not unlike what you do when you get off the coast like that. And so, the good news is New Zealand is here because it's a plate boundary. The bad news is because it's a plate boundary, everywhere in it is susceptible to this style of deformation in all of its different things. As part of the thing I work with the USGS on, instantly after the event, they put together these maps that go on the web for anyone, and this was put together by sort of 6 hours after the event, sort of trying to put it into context. It's not using so much the information right from the event, but showing where it fits along the bigger plates, estimates of ground shaking, previous events, etc. These are some aftershocks. These were recorded down near Oamaru on one of the GeoNet stations. So this starts over here. This is 30 minutes after the event. This is 2 hours after the event. These are all the aftershocks being recorded on a different component seismometer. There's about one every 2 or 3 minutes. So, for the first couple of hours, they were just popping off every minute or two. Most of these were too small to be felt by people, but not, many of them were not. And there were some, I think this one here, this is 30 minutes after. I think most of us felt that one. And then there were some others that went on after that. Well, here's the pattern of aftershocks. This is an animation. Here's the map. The main shock was there. This is going through days. We're now 2 days afterwards. It's popping off. There's some earthquakes out here. They start about 3 days afterwards. Then it sort of moves to the east more recently. This ends a couple of days ago. And I'll play it again. So this is, sort of the way they unfold. And what we see is they don't go in a nice, smooth fashion. There are periods when there are more aftershocks and periods when there are less aftershocks. So if we go back again and do that again, you can see it pops out. Then it sort of hesitates for a few hours, and then it starts off again. And that's, again, very typical. That's not something strange about this event. But the pattern of having 24 hours with fewer and 24 hours with more, it's a stochastic process. These systems are very nonlinear. What triggers them is not really well understood. There may be what people call cascade effects, as one will lead to others, and all of these sorts of things. Okay, our event. Here are these finite fault models for this earthquake itself. These are two different models, assuming the hypocenter, the start of the event, was at either 8.5 kilometers depth or 6 kilometers depth. Right now, we don't really know. It's a little complicated, the beginning of the event. But we see a couple of patches. So this star would be somewhere out in that Telegraph, Highfield, Grange Road area. Any of you who have been to those spots, that's where it would be. But there's a couple of patches of energy, some of it very close to the surface, some of it a little deeper. And so these are things that there may be hotspots of sort of damage associated with this. But also this will then radiate energy in complicated ways. There can be interference, et cetera, that will then play out to produce focused areas of stronger ground shaking and focused areas of less ground shaking. Utilizing these in an engineering mode is just now starting. 5 years ago, it wasn't used at all. The engineers just assumed uniform rupture on the fault. Now, as these are being demonstrated to really represent what's going on, these are now starting to be put into models to try to do a better job of estimating the strong ground motion that can occur during events of this size and larger. And so, we're getting some hint of this. It's coming along. Here's the data fit. I said there's lots of data. It's not just fitting the first arrival. It's fitting, many stations around the world. And, if you had the time, you can look at it. And the fits are pretty good. And so, the algorithms used to determine these things are pretty robust. Now, another intriguing aspect of this, these are those focal mechanisms we were talking about before, that tell us the sense of motion, but there are many ways of determining them. And these particular ways, these two over here, don't just use the way it moved right at first, it uses the entire seismogram. And so it's really getting a measure of what was the motion like that generated the energy that was radiated from the event. And what you see is, although this is sort of looking like one of those things like this with 4 quadrants, there's some complication in it. And this one is sort of the gold standard of these things. It's the global centroid moment tensor. Used to be called the Harvard moment tensor, but then the guys who did it moved from Harvard to Columbia University, and so, and I guess Harvard had, didn't want these turncoats to be associated. I don't know. But one of the things you can do is you can actually decompose this into 2 smaller events. One event is our beautiful strike slip, and what's left over is this little thrust fault. This would have been 5.5 to 6. Now we're getting into the world of speculation. We can use that to say some things. One of the things we can say is that this is a study of the main fault. This tells us how vertical the fault was. If the fault was vertical, it will be right here at 90 degrees. If it's dipping, slanting to the south, it would be on this side of it. Slanting to the north, it's on that side. It's the so-called dip of the fault. The analysis shows that the best fit to all the data globally requires that the fault be about 85 degrees plus or minus. So essentially, almost dead vertical, maybe tilted a little bit to the south. What we noticed was that there was a little bit of south side of the fault tended to be the side that got popped up a bit. That's very consistent with that sort of a geometry. So we know we've got a pretty strike slip fault vertical, which is what this shows. So that means that the residual may make some sense as being something separate. And so one possibility is you could say, okay, we can take this and we can say some of the energies coming from this fellow, the strike slip, the horizontal motion, vertical fault, and maybe this other thing is coming from things like this, these other little thrust faults that we know exist in the region of Canterbury. They've been mapped for decades by geologists at Canterbury University. And so it could be, now, you talk to the seismologists and they say, wow, they would never go forward and say, look for this, because they get laughed out. This is sort of fitting misfit, right? This is taking misfit from this and assigning it to an earthquake. But they say when you start seeing things in the field, that are the right magnitude to be appropriate for that. They say, oh, that's starting to sound sort of interesting. Okay, last thing is the ground shaking itself. Many of you have probably seen these maps. They were produced based on the historic record of earthquakes in the region, estimates of how big the Alpine Fault event would be, and basically they said the ground shaking we would feel in Canterbury was dominantly controlled by the Alpine Fault and the Hope Fault, the thing that goes up the Hope River Valley through Hanmer Springs and all that. Well, they obviously misjudged, because in fact, this area here around us, which is the yellows and blues, which says it should have been about 0.3 G, 30% of gravitational acceleration. In fact, the measurements made all around here are substantially higher than that. There are spots out here that are approaching 1 G, and even throughout much of town, even in areas that weren't amplified by liquefaction, there are ground shaking that exceed that. Okay, so reminding us we are along a plate boundary. Where the plate boundary is affects the reason why we have faults in this whole area. The plate boundary has changed through time. 30 million years ago, this is what New Zealand looked like. It's been moving down to more its present position over the last 30 million years. So, 30 million years ago, all you folks were North Islanders. I know that's, you don't want to know that, but it's only in the last 10 million years that you could have a South Island persona. But so things like the Alpine Fault didn't exist in the same way in the past. They're recent features, but as this side of the plate, as the Pacific is interacting, we build up some fairly complicated regimes. And so we have a really complicated fault system. We have the main Alpine Fault. We have all these faults through the Marlborough area. Here's the Hope Fault, which has a lot of concern about it. But we're sitting down in here, and essentially, it's a scrunch zone. This whole side is moving in this direction, and it doesn't quite fit. And so most of the motion is going to be taken up along these big faults, but this whole area is being slowly but surely deformed. And so the earthquakes, the faults are smaller, they're less often perhaps, but there may be more of them, and as we've seen, because of the whole surfacing of the rivers, the Waimak and these things move back and forth over the last few thousand years, they erase a lot of the data. The plate boundary has changed through time also, and not just the surface fault, but plate boundaries go down 100 kilometers. They're not just at the surface. And where they are at depth is very rarely known, but we have some estimates in New Zealand, and what we think is that the plate boundary at depth is actually offset from the main surface one. So the red lines here are those main surface faults. This is where we would put the plate boundary at depth, and so because of the mismatch between these two, you start getting again, some of this shortening going on. This line would be appropriate for down about 50 kilometers. This line is at the surface. And how you connect those two lines up is basically what's controlling a lot of the tectonics we see, where the mountains are being built, where the fault zones are, etc. And so that says all of this area is susceptible to this sort of scrunching. Whether it will happen again in the next 100 years, we aren't in a position to say, but we should recognize that it isn't so simple that everything applies along those fault zones. Some of the farmers sort of had a view. This is between Highfield and Kivers. And the sun came down, he was up at Massey, came home, and he had his own view about the earthquake. Well, thank you very much. Yes, sir.
On the maps, the epicenter doesn't seem to be sitting on top of the fault line. Why would that be?
Okay, there's a couple of things going on. That's very typical for the original epicenters when they're first mapped, and oftentimes they don't update them. There could be, during the initial rupture phase, there may have been some complexity, for example, some of these smaller faults in the area, and if all of those signals get blended in together, what we do know is the centroid, that centroid moment tensor, which is basically measures the center of energy release. If you plot that on a map, it's dead on where we observe the fault on the surface. So that first order location of the epicenter is a little problematic, but doesn't really, for the seismologists, it's not a big deal because that's not atypical. And they tend to go with the centroid because the other thing to remember is the epicenter is maybe where the fault starts, but it's not necessarily where the energy of the fault is. Most faults start in areas of low energy release. They may be the weakest part of the fault, the easiest to break, and then they propagate. And so if you're thinking about the energy and the deformation, it's really where is that coming from? And that's why the centroid moments, the centroid moment tensors, the location of those become really important because they're telling us where the action is. Yes?
I've been Governors Bay, and the shaking on the 4:35 in the morning was absolutely fierce in the mountains. And can you explain a little bit the propagation of this energy and what happens when this thing meets the foothills?
Okay, there's a couple of things that happen. I mean, the energy goes in all directions, but the fault is then rupturing along, so you can have sort of a effect of piling up of energy if it's propagating toward you, etc. But the main thing I think people saw in some of those issues is what we call local effects. And that is particularly sedimentary basins and the edges of sedimentary basins, you get an amplification. And so I think when you get into areas like into the Port Hills where you're sort of having these basins that are thinning out, the main kilometer deep Canterbury Basin, so to speak, where all the gravels are, as you're getting nearer the volcano and the hard rock of that, you're thinning that out, and that's oftentimes a lot of amplification. Certainly during the Loma Prieta event, that was what was seen as you went from the basins up to where the Santa Cruz Mountains are. Huge amplification of ground shaking right in that transition. As you're essentially, squeezing it down, and the energy then gets converted more vertically.
Do you think that some of the energy could have propagated from the epicenter and sort of ricochet off the Port Hills, and that would have brought it toward the city?
Well, there's been some arguments about deflections. The Kobe earthquake in Japan in, 95? 96? Yeah, 95 was the Northridge, because we were at a meeting, and I was actually, first time I came to New Zealand in January of 95, and there was this, whatever. But that's another story. In the Kobe case, there was some argument that perhaps there was a ricochet off of the mountains there back into the basin. But the other thing, more recently, people have been able, because of improvements in computational capabilities, do true three-dimensional modeling of strong motion in these basins. And it's a tough problem because of the dynamic range you need to have. You need like quadruple precision to keep from your numerical noise for the math guys. But getting back to your question, what we see is that within these basins themselves, there's a lot of reverberation. So the shaking may be lasting longer. They're going to be looking at the strong motion data within the whole Canterbury region to see where the duration of shaking. But when you have these sort of basin-like features, oftentimes you get sort of, it bounces back and forth within them a bit, and it's not that it makes it larger as much as it makes it last longer. And of course, the duration becomes important too, if you're a building or a person.
About the size of the earthquake, immediately after the earthquake, they said it was 7.4. Then they said it was 7. Eventually, they said it was 7.1. How come
Okay, again, the first thing is the difference between the 7.4 and the 7170 is the difference between a moment magnitude and a Richter magnitude. The 7.4 was done very quickly. It's based on using the first part of the seismic record. It overestimated this, and there are potential reasons why that be the case. It's not known, once you get above about a 6 or a 6.5, that type of measurement is known to be problematic. You get saturated and you're matching small things. So that, and that's not atypical either. And of course, one of the problems is, this number gets put out there, and then what does that mean? Right now it's saying 7.1. Those are subtle differences between the way the U.S. Geological Survey calculates the magnitude and GNS Science in New Zealand calculates the magnitude. And there's a bias. The New Zealand ones are always slightly higher. This has been known. For the aftershocks that are being located here is 4.6. USGS is saying are about 4.4. And so this is just, they're using different data sets. The New Zealand data is being using the GeoNet and regional stations. The USGS is using stations further away. So, but most seismologists would say that 0.1, 0.2 difference is within the uncertainties, and so one shouldn't make a big deal about that. And so you'll hear, the USGS says 7.0, GNS says 7.1, and everyone says, yeah, that's fine, that's within our ability to discern. Yes, sir.
What was the relationship for the initial earthquake, the one that was felt on Wednesday morning, which was published at the centre of somewhere near Littleton?
Okay, typically in the aftershock sequence, there are sort of two types of aftershocks. So when the fault initially moves, there are sections along the fault that are not in equilibrium anymore. And they can have aftershock. They are typically the early aftershocks. There are patches on the fault that maybe didn't quite move enough. And so the early aftershocks, and if you looked at that video, they tended to be clustered. And we actually can use that to say something about how long the fault was. The first 12, 24 hours or so, you tend to have most of the aftershocks very near the fault, either on the fault or in the rocks on either side. Over time, what's happened, though, is as these two, you remember, it's not just movement on the fault, but everything north of the fault went one way and everything south of the fault sort of went somewhere else, but the fault's only 30 or 40 kilometers long, so when you get to the ends, there's a pile-up situation. So over time, and particularly, a few days later, a week later, the aftershocks tend to be more off the ends of the fault or in the surrounding countryside. So we had there were some earthquakes off to the west, and there were also to the northwest over by the Waimak. And then we had the stuff in the Port Hills, Governor's Bay, and things over to the east. And that's pretty common with aftershock sequences. It doesn't mean they stop along the fault, but you start picking up these ones that are away from the fault, and that's essentially a stress transfer, that you've moved the locus, so you've sort of released it all along the fault, and now you've pushed it into what was stuff that was plenty happy before the earthquake and now is sort of being stressed, like the people who are living there.
I've heard some speculation about the orientation of the fault and in relationship to the known fault zone in Erskine Bay. That with Christchurch lies somewhere in between. Are we in a position to comment on that any further?
What we know, there's been a bunch of studies done to look and see whether faults propagate across discontinuities of distance. And basically, it depends on the length of the fault. A study was done sort of looking globally. I mean, this is just looking at the history, not theoretically. But the length of the fault versus the amount of offset you could have to another fault to have the next one sort of triggered by it. And for a fault of this length, any fault that would be more than about 2 to 3 kilometers discontinuous, set aside from this one, don't get triggered. The studies have shown that, if you have a fault the size of the Kunlun fault that runs through Tibet that went for 700 kilometers, then it can transfer energy onto faults that are 20 kilometers away or so. But faults of this length, 30, 40 kilometer, 50 kilometer, 100 kilometers long, for another fault to sort of become engaged in that fault's behavior. Now, to say that, so there doesn't appear to be, based on the historic record globally, a link. As a person who's worked a lot with faulting and seismology, we're always very uncomfortable to say this fault isn't going to rupture. My comment would be any fault anywhere in New Zealand can have the potential. You're a plate boundary. Any fault has the potential to rupture. If it happens soon, people will try to make the link that it's somehow correlated with this. I've heard people trying to argue that the earthquakes last week in Hawke's Bay were somehow related to this. And, I don't think there's much validity to those things. But, the record shows that there shouldn't be a direct link because of the distance of the offset.
What about the 3 that in Kaikoura?
Well, Kaikoura has earthquakes all the time. Small ones like this. All the time, meaning if you look on a map, it's at the southern end of the subduction. Whether those are related, it always catches our eyes, and the thing is, if you go back, I bet if you went back and looked at the history, this is what I've had students do in classes. Whenever there's been an earthquake, every earthquake that happens gets recorded, gets reported big time, right? Wellington has magnitude 3 events daily almost. And they're big. So, I'm not trying to say they aren't relevant, but we have to worry and make sure that we're not seeing a biased record. And it could be, right now we don't have a good reason to argue they're related, but the fact that there are events in Kaikoura is not surprising to anyone based on the normal background seismicity. Yeah, okay, you always feel uncomfortable because I don't want to say they are or aren't related. Yes?
The earlier map you showed, you had the Alpine Fault is along the plate boundary.
Yeah.
There's the depression zone. Does that mean if there's another earthquake in this region sometime in the future, is it likely to be on the same fault line, or would it be an entirely new fault line? It's not like the Alpine Fault.
Yeah. That's a first-order research question that people don't have a good answer to. The normal assumption is that it probably would not be on the same fault line, but it doesn't mean that a fault 10 kilometers away or 20 kilometers away couldn't be involved. But we really don't have enough of a record. It makes theoretical sense, and if you do your modeling of sort of stress relaxation and things like that. But we're also talking about elastic media, and elastic media don't really have a memory in that same sense. And so we don't think there's not. When you look at most faults, that doesn't seem to be the case. But it doesn't mean that Canterbury doesn't have a continued earthquake risk. It means that, fill in the blank type thing. So I think, it is different, though, from a plate boundary or a well-established fault like the Alpine Fault or the Hope Fault that have a history of repeated events on the same structure. And those are mature faults that tend to dominate. These less well-developed faults, a lot of my work's in Northern California, and we have the same situation there. As you get to the northern end of the San Andreas system, we have lots of little faults, 20 kilometers long, 30 kilometers long, and trying to figure out whether they're going to repeat over 50 or 100 or 1,000 years on the same structure or bounce around is a really tough question. Yes?
There's a man named Ken Ringley brings out an almanac that says that earthquakes are more likely to happen related to phases in the Earth or other factors. Has anybody actually ever looked at that?
Yes, that's been looked at a bunch of times, and it sort of gets looked at, and then new data become available. The argument there is that tidal forces associated with phase of the moon, and the same way we have tides in the ocean, we actually have tides of the Earth's surface itself, the Earth bulges, etc. And so people have looked at that. The level of stresses that are caused by it are quite small, orders of magnitude, hundreds or thousands of times smaller than the type stresses associated with the earthquakes themselves. Most of the study, they've done the physics sort of studies don't seem to work. So people have also done the statistical studies to look for patterns. And so far, none of them have passed the test of there appearing to be a pattern. Now, those of you who are into statistics know better than I the difficulties of working with small data sets and trying to do statistics on small data sets, et cetera. And so that continues to be a question that keeps coming back. So far, there's never been any, every test of it, it has failed, the test. That's not to say that perhaps with a more complete data set, that could change a little bit. But I think the common view right now is that that's not, that doesn't appear to be a useful tool for trying to identify times of more likely earthquake activity or not.
Please allow me to ask the last question, and then we can go ahead here on the fourth floor. Can we go a bit proactive on this? Can we make some underground explosions along fault lines every 50 years to release the stress? Avoid accumulating to some gravity.
Well, people have, that idea has actually been proposed, particularly on known fault lines. One of the things we know that is that if you pump high pressure fluids into a fault zone, you can release what we call the normal stress or the confining pressure, which would potentially allow them to slip. So people proposed drilling into the San Andreas Fault and pumping fluids down to trigger events. It's not been done for a variety of reasons. One is we really don't understand, we understand the physics of fault propagation quite well. The physics of earthquake nucleation is not well understood at all. And actually, whether this is something you have to go from a sort of a molecular level up to the rock level, etc. So the question is that you could drill this hole and pump lots of fluids down or put a bomb down or whatever, and you may accomplish nothing. The other thing, though, is although we also understand how faults propagate, the two big questions in the sort of the fault propagation world are nucleation and stopping the fault. Because faults don't go forever, they stop. And I said one of the things has demonstrated that if there's a large enough step over, they seem to stop. So when it's more than a couple of kilometers, a fault will stop and doesn't continue on to the next one. But we don't know what causes them to stop. And so the problem is we don't know that if you started an earthquake, it would stop at a magnitude 5.5 or 6 rather than grow bigger. The last point is that it's important to recognize that the energy associated with these events, the displacements, scales logarithmically. So, a magnitude 7 represents 10 times more ground motion than a magnitude 6. But it also represents 30 times more energy than a magnitude 6. So you would need a lot of smaller events to deal with releasing all of the, a small event wouldn't be 2 billion millibars. And the Earth needs those, and so that's the problem. So it's one of these things people talk about. Some of the calculations have been done. I don't think anyone would want to be the one to actually implement it, unless they have really good insurance.
So thank you for a fantastic talk.